Assalamu alaikum. We are going to just start with the more example for the homogeneous higher order differential equation. This is for part 3. Part 2 we have done already. And here the important thing is that when we want to solve the homogeneous differential equation of the higher order, we must not forget that we always write our substitution y is equal to e to the power mx. This is our substitution for solving the problem. This is the constant coefficients. So then we are having here y dash. Y dash is m e to the power mx. And our y double dash, the second derivative, is equal to m square e to the power mx. When substituting in a differential equation, as I mentioned, is ay double dash plus by dash plus cy equal to 0, then our characteristic equation will be am square plus bm plus c equal to 0. That will be our characteristic equation. That is very interesting. We replace y double dash with m and y dash with y double m square with m and y with 1. Now here we solve this equation and we get two roots. We're having m1 and m2 other roots. So they are the solution depend upon the nature of the roots. The roots are real, they are not equal. In one case, roots are real but they are equal, and roots are, this case 1, we say this m1 and m2 are real and m1 is not equal to m2. So we write here y is equal to superposition of the solution c1 is e to the power m1x and c2 e to the power m2x. So we are having here two linearly independent solutions, and we case the superposition of this one. Case 2 is that we are having two solutions m1 and m2, but here m1 is equal to m2. So when I write my y in the above way, that we having two, so we are having here m1 equal to m2, so we get here c1 e to the power m1x and plus c2 e to the power m1x. So we take e to the power m1x common and c1 plus c2 become another constant. So we don't have two arbitrary constants in this case. So here in principle we have one solution, and then we use the reduction of order formula for that one, and we get the second solution. And very interesting there, when we find the second solution, then we are having here in that case just change in that one by using that formula, that we multiply our second solution by x. Now they become two solutions, though two linearly independent solutions. So when our roots is repeated, we multiply always with x. So that we have to remember that one. And number 3 is that we are having here solutions, they are complex. The complex solution is in the form of the alpha plus minus iota beta. Alpha is our real part and beta is our imaginary part, and we have seen it last time that when we in our part 2, that when this is, then how we write the solution. Our solution y will be equal to e to the power alpha x. We get here c1 cosine beta x plus c2 sine beta x. That was the part we have done already, and that we have just has revised, and we apply this one for solving our initial value problem. In initial value problem, as mentioned before, we're having the differential equation. This is our differential equation, and then we can have here the initial conditions. So we're having the initial condition differential equation, then plus initial condition, we say is initial value problem. And if we are having here instead of initial conditions mean what? The condition at the same point. Whether it's condition at the point x equal to 0, both of them. If they are two different points, that's here x equal to 0, x equal to 1, x equal to minus 1, two different points, then this condition we say boundary condition. Then boundary conditions, when we have the differential equation and we have the boundary condition, the condition at two different points, we call this one as boundary value problem. So we use this initial conditions or the boundary condition to find the value of the constants. These are, for example, we have the equation, we are having here two constants, or we can see here there are two constants, and we want to find the value of this constant, and we substitute. We first get the general solution and we get the value of the arbitrary constants, then we say we get a particular solution. So here we start again as before. We take the substitution y is equal to e to the power mx, and we substitute in our equation, we get the characteristic equation I hope you have done a lot of practice and you can see and understand it very easily that how we can find the characteristic just replacing y double dash by m square and then y dash by m, and then we having 5y by 1 equal to 0. That's the quadratic equation. Want to solve, we factorize this quadratic equation. You can see it here. We can't divide m2 in two parts so that we get here 2. No, it's not possible. So we use the formula, the quadratic formula, that our m is equal to minus b plus minus under the root of b square minus 4ac over 2a. Now my a is equal to 1, b is equal to 2, c is equal to 5. So substitute here, b is equal to 2, we get here minus 2, plus minus under the root of b square, that's 4, minus 4ac. 1 multiplied by 5 multiplied by 4 is minus 20, over 2a, a is 1, so we get here 2. So we further simplify this one, we get here minus 2 plus minus under root of minus 16, and here is divided by 2. So when we take here under root of minus 16, we can just write this equal to under root of 16 iota square, because here minus 1 is equal to the complex value iota square. Now this will be equal to 4 iota. So we can write here this equal to minus 2 plus minus 4 iota over 2. We simplify further, we have minus 2 over 2, then plus minus 4 iota over 2. Simplify it further, we get minus 1 plus minus 2i. So I get here the values, that's the values of the roots. The roots are having the complex values, and we having here these values as we can just write that we are having here the values. The real part is alpha equal to minus 1 and beta equal to 2. So we get here this minus 1 and this is my 2. So here now in my position to apply this number 3, the roots are alpha plus minus iota beta. I put here the value of alpha equal to minus 1, beta equal to 2. So I can write my solution. My solution in this case will be equal to y. We're having here e to power alpha x, that's minus x, c1 cosine beta x cosine 2x plus c2 sine beta x sine 2x, and this is my general solution, solution of my differential equation. Now the next is that I want to find the particular solution. So find the particular solution, what I will do, I will use this initial conditions to find the values of C1 and C2, and then when you put the values of C1 and C2, then our solution will be a particular solution. So to do that one, we having here using this initial conditions, using initial conditions. One condition is very straight, that we having the value of y when x equal to 0, y is equal to 2. I substitute in my equation x equal to 0. X equal to 0, this becomes 0. Y is equal to e to power 0. We get here c1 cosine 0 plus c2 sine 0, and this is equal to what? This is equal to, here this is not 0, this is 2, is equal to 2. Now we know that the value of sine 0 is equal to 0. The value of cosine 0 is equal to 1. Use these values. And e to power 0, anything power 0 is equal to 1. So we'll get here the result here, this is equal to 1, this equal to c1, and this equal to 1, this equal to, so we get here c1 is equal to 2. This is the value we'll get here for our the first arbitrary constant value is c1 equal to 2. We have used first condition. We come to use second condition. When we want to use second condition, then we having here dash. That means the derivative. So it means we take the derivative and then we apply the conditions we find here. Now y dash, taking derivative of this one is the first function, is the second function. First function derivative of second function, we get here e to power minus x. Derivative of second function, derivative of cosine 2x is minus sine 2x, then derivative of 2x is 2. So get here minus 2 c1 sine 2x and plus 2 c2, derivative of sine is cosine 2x, then plus derivative of the first function e to power minus x, that will give here this equal to minus e to power minus x, and here we get c1, our function here is C1 cosine 2x, C2 sine 2x. C1 cosine 2x plus C2 sine 2x. So here we get over the derivative. Now we can apply our condition. Our condition is when x equal to 0, y dash equal to 1. Our condition is when x equal to 0, y dash is equal to 1. So we can here y dash at x equal to 0 will be equal to, we can put it here like this one. At x equal to 0 also we can write here the value of y at x equal to 0. We can write like that. This is equal to e to power minus 0 minus 2c1 sine 0 plus 2c2 cosine 0 plus here is minus e to power 0. I am having here c1 cosine 0 plus c2 sine 0. Let me simplify this one. Sine 0 is equal to 0, cosine 0 equal to 1, e to power 0 is 1. So, and this is equal to 1. The value of the condition that y at x equal to 0 equal to 1. Now it is simplified. This will be 0, this will be 1, this will be 0, this will be 2c2. Then plus, here is minus sign, so get here minus, this is equal to c1, and this will be 0, and this will be equal to 1. So we get here 2c2 is equal to 1 plus c1. I have the value of c1. What's my value of c1? c1 is equal to 2. So I get this equal to 2c2 is equal to 1 plus 2 is equal to 3. What's my c2? My c2 is 3 upon 2. So I get the values of the constant c1 and c2. I substitute the value of my constant in the general solution. I can write here my particular solution is, I have the constants and now I am in position to write the critical solution where y is equal to e to power minus x. The value of c1 is equal to 2 cosine 2x plus 3 by 2 sine 2x. So that's the solution of my problem.